Okay, let's spend a few minutes proving the Pythagorean theorem together, and actually its converse. But before we do that, let's understand why is it called the Pythagorean theorem. Those sounds like big words. Well, theorem just means rule in math. So we have a rule, and it was actually invented or discovered by this mathematician in ancient Greece named Pythagoras. And that's why it's called the Pythagorean theorem. Okay, now we can prove this theorem just like Pythagoras did. There are several different proofs. Let's try one that uses a diagram like this. Okay, so what I've done here is I've set up a big square, and inside there's a little square. Okay, the little square has dimensions c by c. Okay, and then the big square has dimensions a plus b by a plus b. So each side of the big square is a plus b. And what that does is it forms four triangles. And what can we say about those triangles? Well, we know they're all right triangles because they all have the right angle that's at the corner of the square. And we know that each of the triangles has the same side lengths. It has legs of length A and B. Remember, legs of a right triangle are the ones next to the right angle. And then a hypotenuse, that's the side that's opposite of the right angle, of length C. So every single one of these triangles has the same dimensions, legs of A and B, and a hypotenuse of C. Make sense? Okay, so now let's ask ourselves, what is the area of this white space in here? Well, you say that's just a square, so it's C times C or C squared. So let's write that. Okay, now what we can do, if you were to take this diagram and you could cut it out, and rearrange the different shapes within it, you could create a shape that looks like this. Okay, now let's see what this shape is. It has the same four triangles, and what we've done is we've just arranged them differently. We've stacked up two of the triangles here and two of the triangles here. But you can see they still have dimensions A and B as the two legs, and C as the hypotenuse. We just moved them around. And what we've done is we've done that in such a way that we've still created a same-sized big square. Okay, same size as this over here. How do we know that? Well, we can see that this is length A, and this right here is length B. So this is A plus B here, A plus B here, A plus B here, A plus B. Just the same as this square over here with sides of length A plus B. Okay, so what we can say here is that, this is the exact same big square, but let's ask ourselves the same question that we asked about this, which is, what is the area of the white space? Well, there's two squares that make up the white space over here. One has A as its side length, and one has B, and we know that this square then has the area of what? Yeah, that would be A squared. And how about this one? Yeah, that would be B squared. So we can write the area of the white space here as A squared plus B squared, right? But we also know that these are the same four triangles, and so the white space over here must equal the same white space here, because together the white space and the triangles make up the same square, right? So we can say that this white space is equal to this white space. And let's go ahead and write that. So C squared must be the same as A squared plus B squared. Now, usually we write the Pythagorean theorem in just the other order. It's the same equation. I just flipped the sides here. And I put it in bold because that right there that you're looking at is the Pythagorean theorem. A squared plus B squared equals C squared. What does it mean? Well, it means for any right triangle, so this only works for right triangles, the sum of the squares of the measures of the two legs, that's a long way of saying A squared plus B squared, will equal the square of the measure of the hypotenuse, C squared. Any right triangle, that works. Okay, great. So now you've proven one of the most important theorems in all of mathematics, just like that. And now let's also prove what's called its converse. Okay, a converse is kind of going the other direction. So what we're going to do instead is, instead of saying, if we have a right triangle, let's prove that A squared plus B squared equals C squared. Instead, we're going to say, if we have a triangle with A squared plus B squared equals C squared, it is a right triangle. We're going to try to prove that as the theorem here. So I'll go ahead and state this in words. If a triangle has the sum of the squares of the measures of its two legs equal to the square of the measure of the hypotenuse, so in other words, if it has A squared plus B squared equals C squared, then it is a right triangle. Okay? So let's just say that in simpler language. If a triangle has A squared plus B squared equals C squared, it is a right triangle. That's what we're trying to prove. Okay? To prove this, I'm going to set up two triangles here. Triangle A on the left is a right triangle. That's why it has the right angle written in there for angle 1. And it has leg lengths of A and B and a hypotenuse of C. Okay? So that's triangle A. Triangle B is a little bit different. It has A and B and D as its third, but we didn't put in a right angle because that's what we're trying to prove. Okay? So first let's ask ourselves on triangle A, what can we say about it? Well, it's a right triangle, so we can say that a squared plus b squared equals c squared. We know that from the Pythagorean theorem. Now what we're going to do with triangle B in order to prove the converse is we're going to say a squared plus b squared equals d squared. Okay, we're just going to say that. And we're going to say if that's true, can we then say that angle 2 is a right angle? That's what we're going to be trying to prove, okay? So what we're saying this one is true because it is a right triangle, and we're assuming this is true to see what that means about angle 2. Well, if a squared plus b squared equals c squared, and a squared plus b squared equals d squared, and these a's are the same and these b's are the same, we're setting up the triangles that way, then c squared has to equal d squared, right? Because they're both equal to a squared plus b squared. So let's write that, c squared equals d squared. Well, if c squared equals d squared, then we also know that c equals d, right? Now, let's remind ourselves of one thing. Triangles that have all sides equal are congruent, and congruent triangles have angles of equal measure. Well, we just proved that C and D are equal. We know that A and A are equal and B are equal. So these two triangles, A and B, have all of their sides equal. They have all their sides equal, so they are congruent. So A and B are congruent. Well, if they're congruent, they must have angles that are also of equal measure. So this angle up here must have the same measure as this angle here. Same with this one and this one. And this is the most important for our proving of the converse, this angle right here must be the same as this angle here. In other words, the measure of angle 2 must equal the same as the measure of angle 1, so measure of angle 2 must be 90, just like measure of angle 1. And then we can say, well, if that's true, then triangle B is a right triangle. So that's proving the converse of the Pythagorean theorem. So just in about 7.5 minutes, you've proven one of the most important theorems in mathematics and its converse. Great job.